Okay, so what I'm doing here is just walking through the solution to the first homework. And, as I get time, I'll do more detailed solutions like this one. Sometimes I'll just do handwritten ones and PDF them. I've noticed that if I use handwritten notes and scan them and try to talk over them on the screen, the resolution doesn't work. The screen capture comes through and it's pretty fuzzy. So I'm not sure the narration is going to work most of the time. But let's try it. What I did here was I actually typed out the solution. And there's a separate PDF you'll find on Blackboard of those type solutions. But then I cut and pasted into this little slideshow. So problem one was one I gave you. It wasn't from the book. And I said, given how much energy, how much electricity we use in this country, how much land area would we need to cover with solar panels, to dedicate to solar farms, to create that much energy? And keep in mind that I didn't take into account things like when the energy is produced and things like that, and where it's produced, which really matters to the grid. But for now, let's just go with these broad numbers. So I gave you these numbers that came out of the information that I presented in the first lecture. 4.05 times 10 to the ninth megawatt hours per year is how much electricity we use. I looked up, I found a couple sources, and this is not bad. I've gotten anywhere from 10 acres to 7 acres per megawatt of capacity. So if you have a solar farm that's rated at 1 megawatt, it would occupy about 7.5 acres. That's a round number. And if you're down in the southwestern United States, like New Mexico, you can count on a capacity factor of about 0.2, maybe even a little higher. Okay, so an intermediate step there is figuring out how much energy, how many megawatt hours of electricity we get for a megawatt of capacity. And so very simply, we know that the capacity factor is 0.2, so it's 20% of what we'd get if that megawatt could run full-time 24/7. So it's a megawatt of capacity times 8,760, which is how many hours there are in a year. 20% of that is 1,752 megawatt hours per year for every megawatt of capacity. So you can kind of combine a couple of facts together and say that means for 1,752 megawatt hours of electricity in a given year, we'd have to dedicate 7.5 acres to that. So we've got enough information now to just pretty much do a simple math calculation. Go back to our original, and it's 4.05, not 4.04 as I show here, times 10 to the ninth megawatt hours per year. That's how much electricity we need. And then we know for every megawatt of capacity, we get 1,752 megawatt hours in a year. Multiply that times 7.5 acres per megawatt of capacity, and we get 17,337,000 acres of land we would need. Sounds like a lot, but that's why I asked you to do the next step, because 17 million acres, well, sure, that's a lot, but how much is that really compared to, say, how much land we have in the western United States? So New Mexico, you can look it up, Google it, 121,697 square miles. There are 640 acres in every square mile. So that means New Mexico's about 77 million acres in size. Do the quick division, that's 22%, but a tad under a quarter of New Mexico we'd have to cover in solar panels, which is an awful lot of land. But keep in mind that how much of New Mexico are we currently using? Probably less than 22%, for our own development. So there's a lot available too. I mean, it's sagebrush and there's habitat and there's lots of things to take into account. But the point is, it's entirely possible. Okay, 1.2 in the text. That's the second problem for the homework. In this problem, the author says that a kilowatt photovoltaic array would generate about 1,700 kilowatt hours. So implied in that statement is a capacity factor, and that's the first thing we'll look at. That's the first part of the problem. So that means if it's a 1,500 kilowatt hours in a year, it's a 1 kilowatt capacity. That's 1 times 8,760. Do the math, and it's about 0.17, so 17%. A little bit lower than what I said in the last problem. But in the last problem, I was actually thinking of the southwestern United States. This is a broader U.S. average. So the question is, what's the potential that some studies say the potential for rooftop solar is about 1,000 gigawatts of capacity. And then they say, well, how many Rosenfelds does that represent? So if you read the book, on page 31, we talk about this unit that somebody suggested we represent. It might have been Mr. Rosenfeld, I don't know. It says it's a unit of energy that if we could produce that unit of energy renewably, carbon-free, it would displace the amount of CO2 emitted from a coal plant making that same amount of energy. So it's sort of, a Rosenfeld is how much renewable generation, in this case solar, it would take to displace the energy created by one coal plant. And they already figured that out. That amount of energy is about 3 billion kilowatt hours per year, 3 times 10 to the 9th kilowatt hours. So how much are we talking about from rooftop solar? So we want to know how many of those Rosenfelds, how many units of 3 billion kilowatt hours we will be able to generate with 1,000 gigawatts of capacity of solar. And remember, we already had a capacity factor of 0.17. So I just go through the math here. 1,000 gigawatt capacity, that's how much studies have shown we could put on roofs. And I do the conversion from gigawatts to kilowatts. You need to, I know this is confusing. Megawatts, kilowatts, gigawatts. We'll probably have terawatts somewhere along the line. Just be careful. Keep track of it. And then we have 8,760 hours in a year, and then we got a capacity factor of 0.17. So that means that if we completely build out all the potential for solar, the solar rooftops, that 1,000 gigawatts of capacity, we can count on that creating about 1.5 times 10 to the 12th kilowatt hours in a year. Again, that's a big number, but the neat thing about this unit of the Rosenfeld, it lets you look at that number and get a sense of what that means. What that means is, if you do this conversion, that one Rosenfeld is 3 times 10 to the 9th kilowatt hours. That tells us that the full build out of solar rooftop is about 500 Rosenfelds. That means that build out would replace or displace the energy currently created by 500 average coal-fired power plants in the country. So that's kind of a better, I think that's a better unit, a better way of looking at it versus saying 1.5 times 10 to the 12th kilowatt hours. That number doesn't mean a whole lot. 500 coal plants, yeah, then you can get your head around that. Okay, 1.3 in the text. So we went through, we want to know what would be the impact of a carbon dioxide tax. This is something that shows up on the federal level. It shows up worldwide periodically. So let's say somebody's proposing a $50 per ton. And notice I spelled ton funny because that's a metric ton. That's 1,000 kilograms. Somebody's proposing a tax of $50 per ton of CO2. How much would that add to a cost of a kilowatt hour of electricity? And of course the answer to that depends on how it's produced. If it's produced renewably, the answer to that is 0, right? Because it doesn't impact that. But all the fossil fuel conversion techniques result in the emission of carbon dioxide. So we have to walk through that, and it all depends on the heat rate of the power plant and the fuel that's being used. So here's a couple bullet points that you need to keep in mind as you work on the problem. A BTU of energy is equal to 1,055 joules of energy. Combustion of coal results in the release of about 24.5 kilograms of carbon for every gigajoule of energy released. Combustion of natural gas results in less carbon per gigajoule, about 13.7, kind of half roughly. And then the assumption we make is that carbon is released in the form of CO2, and there's a ratio. There's 44 kilograms of CO2 for every 12 kilograms of carbon. We went through that in class. It's the molecular weight of carbon, atomic weight of carbon versus the molecular weight of CO2. And again, 1 metric ton is 1,000 kilograms. Okay, so here's just that expression. So what's the impact of that CO2 tax, that $50 per ton CO2 for a coal plant with a heat rate of 10,500 BTUs per kilowatt hour? And it's just following the units, right? I'm going to bring the cursor in to walk you through it. I hope you can see it on the YouTube. There's the heat rate. Here's that conversion factor of joules to BTU because I wanted to get rid of the BTUs and go to joules. Here's the carbon to energy ratio for coal, 24.5 kilograms of carbon to gigajoule. There's that ratio of CO2 to carbon emissions. And there's the tax, $50 or 5,000 cents per 1,000 kilograms of CO2, metric ton. And the answer to that is 5 cents per kilowatt hour, which is actually, as I pointed out in class, a significant amount when people pay. We pay some of the lowest rates in the country on around 7 or 8 cents, but even, up in the Northeast, it doesn't get much above 15 to 20 cents a kilowatt hour. So that's a significant increase in the cost. But keep in mind that not everybody gets all their energy from coal power plants either. So as we go through this, and we've had 5 different power plant and fuel combinations to look at, the things to keep in mind are the heat rate, they change, and then this factor here, which is the carbon per joule ratio, which is different for coal than for natural gas. So not boring you can go through all of them together. It's not that surprising. We get this table that the traditional pulverized coal, which is the worst one of the group, that creates an increase, results in an increase of about 5 cents a kilowatt hour. A better coal plant, one that's built today, has a lower heat rate. It's more efficient. That's 4 cents. IGCC is integrated gasification combined cycle, so that's a higher efficiency plant. There's only a couple of these operating in the country. They're experimental or in demonstration phase. The advantage of an IGCC plant is that it still creates a lot of CO2, but it does it in a separate stream. It's not diluted in all the other exhaust gases. So if we want to make the step to carbon sequestration, that's the technology to use. That's a little bit worse than a new coal plant. Natural gas combined cycle is 1.8 cents a kilowatt hour, so that's the best. So this is Langley Gulch, by the way, is a natural gas combined cycle, so it falls into that category. And then the simple cycle natural gas, which are like the peaker plants near Mountain Home on I-84. They're not as efficient as the combined cycle, so they have a higher impact for the carbon tax at about 2.5 cents, which of course obviously is only half of what it is for a traditional coal plant. Okay, the last problem, 1.5 in the text, is getting at what happens if we were to replace all of the coal plants with a nice efficient natural gas plant. So still fossil fuel, still fuel that we have available in the United States, it's just cleaner. How much impact could that make? Well, they come up with some numbers here for us. There's 300 gigawatts of coal-fired capacity. We call that the nameplate or capacity. And altogether, they generate about 2 million gigawatt hours of energy in a year of electricity. And they're responsible for emitting about 2 gigatons of CO2. So the capacity factor is about 0.76. So that's the amount of energy, the 2 times 10 to the 6 gigawatt hours, divided by the capacity, 300 gigawatts, times the number of hours in a year. So if they generally run at full capacity, it means they're on average available about 3/4 of the time, 76% of the time. So what if we replaced all that capacity with a natural gas combined cycle that were 50% efficient? And the important part of this problem is realizing when they say it's 50% efficient, they're telling you the heat rate. If it was 100% efficient, the heat rate would be 3,412 BTUs per kilowatt hour, because that's the conversion factor between BTUs and kilowatt hour. If it's 50%, that means there's twice as many BTUs for every kilowatt hour as there would be for 100% efficient. So that's where we get 6,824 BTUs per kilowatt hour for heat rate. And once you know the heat rate, it's right back to the problems we did before about, well, what's the CO2 emissions for all that capacity? So I won't bore you with that, but the answer is about 0.72 gigatons of CO2 per year. Out of the total emissions for the U.S., which is 5.8 gigatons, so if you add up all the coal and all the natural gas power plants in the country, they're responsible for about almost 6 gigatons per year. What percent of reduction would that represent? Well, you take the 2 gigatons that we had before, you subtract the amount of emission you get if we replaced them all, and that's 0.71, so that's about 1.3-ish. And divide that by the total of 5.8, so that's a 22% reduction. That's a lot, that's a great deal of reduction, and probably I'm sure somebody's thinking about what it would take to replace the coal plants. So that's it. That's homework 1. This is typical of the kind of analysis we need to do with renewable energy, of kind of just, it ends up being just tracking units. Make sure we understand our vocabulary. What's a capacity factor? What's capacity? What's an emission rate? So those sort of things. So it's I think a good first step in this class, and letting us know what we're going to need to be looking at. So that is it, and we'll see you soon.